Hello, everyone. Can you hear me? Excellent. Thank you very much. I'm sorry I'm not able to join you in person. It looks like a great conference happening in Prague, and I hope you're all having a good time. So I'm pleased today to talk to you about our work in the Open Quantum Safe project. I just want to make sure my slides are coming through full size. I think there's there we go. Wonderful. All right. Yes. So a little bit of background first. For me, OpenSSL has a very important place in my heart. OpenSSL was actually the first open source software project that I contributed to. In 2002, I made my first commit, which I think involved emailing a patch file to an email address. So times have changed since then. And this was included in OpenSSL 098. So I was really proud of this at the time. I was doing this while I was an intern at Sun Microsystems, and we were working on a project to evaluate elliptic curve cryptography, which at the time was the next generation of cryptography. And we were working on a paper benchmarking elliptic curve cryptography in TLS, and we did that by making an integration with OpenSSL and then contributing that to the OpenSSL project. And for me, there's a direct line from this to my work on post-quantum cryptography and the Open Quantum Safe project. So about a decade later, some colleagues and I were starting a project to look at key exchange based on the ring learning with errors problem. We wanted to see how it worked in key exchange, pick some parameters, evaluate in TLS. And so for me, this was a time to revisit this work that I did, including the contribution to OpenSSL, to look at adding a new algorithm to OpenSSL to benchmark it. And this is really the seeds of the Open Quantum Safe project. I decided to post my fork containing this ring learning with errors key exchange on GitHub, and this is where our project grew from. So the Open Quantum Safe project, in case you're not familiar with it, is centered around a core cryptographic library called libOQS, which brings together under a common API post-quantum key exchange or key encapsulation mechanisms, as well as signature schemes. And we have schemes from 4 of the 5 main families of post-quantum mathematical assumptions. On top of this core library, we have a variety of integrations into other major libraries and languages, and most notably being our OpenSSL 3 provider, as well as some demo integrations into other tools. And then we show how to use these in a variety of applications. So in the talk today, I'll tell you a bit more about what we're doing in the Open Quantum Safe project and where we're going with that, how it connects with OpenSSL, and also talk about some of the other projects, some of our sister projects, such as the post-quantum code package. Okay, so the center of our project is libOQS, which, as I said, is a C language library that has a common API for post-quantum signature schemes and key encapsulation mechanisms. It's open source, primarily licensed under the MIT license, but also others for certain components, and builds on a variety of platforms. And we've been working on this since 2016 with a wide variety of contributors. And I've got some of their faces here, but we've been fortunate to have many people involved and many organizations involved over the life of our project. When I was preparing this presentation, I was curious to go back into our GitHub history and see how many different algorithms we've supported over the time. So overall, we've supported 33 different post-quantum algorithms over our history. And not all of those continue to be supported today, but a surprisingly large fraction of them are still in play. And so as of now, we support a variety of standards track and experimental algorithms. Currently, we have support for 18 different families of post-quantum algorithms. We have support for the NIST standards, MLChem, MLDSA, and stateless hash DSA, as well as the related IRTF standards, the stateless hash-based signatures, LMS and XMSS. We also have support for NIST selections for future standardization, Falcon and HQC, and algorithms that are going through standardization at other bodies, like the ISO draft standards, Classic McLeese, and PhotoChem. We're trying to support algorithms from the NIST signature on-ramp. We have a few of those in the library right now, but we'd like to see more of those to continue to support experimentation. And we have a few other algorithms that we're supporting as well because of interest in certain applications or certain use cases. So overall, we currently have, I think, 326 algorithm variants available in the library across these 18 algorithm families. In terms of where the library is right now, we are providing constant time testing of most of our algorithms using Valgrind. And as part of our testing suite, we do have ACVP tests for the NIST standardized algorithms, MLChem and MLDSA. And some third parties have received certificates for CAVP testing of MLChem in libOQS. Looking for the forward direction of our project, our primary focus continues to be on supporting research and experimentation. So at this point in time, we don't have any plans for seeking FIPS validation of the library by our team, for example. One of our main focuses is to continue to keep algorithms up to date. So we have plans we would like to update the standards track algorithms as those evolve. So when Falcon and HQC have initial IPD, initial public draft documents for the FIPS standards, we will look forward to updating those, as well as making some updates to PhotoChem. We'd like to support more MLDSA options. There's a variety of options like external mu or pre-hash or deterministic signatures. We'd like to see support for that. And we'd also like to integrate formally verified decode into the libOQS. We'd like to continue to support more schemes from the signature on-ramp currently in round 2 of the NIST evaluation. And we'd also like to improve our testing. We have an internship project going on right now to extend our constant time testing to more platforms. We'd also like to explore how we can use the data-independent instruction features of CPUs. But we're really looking to grow our contributor community to help achieve these future directions. So if you are interested in any of these or have your own ideas, we'd love to hear from you and see how we can get you involved. One of the main use cases of our project has been for testing and evaluation of integration into the TLS protocol. And so when we started this off, we were doing this by making a fork of OpenSSL and continuing to patch that fork to add new algorithms and to keep in touch with upstream updates. But this has been made a whole lot easier by the new provider architecture from OpenSSL 3. And so our focus now is providing integration into TLS and other applications via the OQS provider. So this is an OpenSSL 3 provider that adds support for all of the post-quantum algorithms in libOQS to OpenSSL 3 and higher using the OpenSSL 3 provider architecture. And there's an incredible amount of work done to put this together by Michael Bench and a variety of other contributors. And we're really grateful to the work of the OpenSSL team in expanding the OpenSSL 3 provider architecture and in helping diagnose our problems when we ran into them working with the new provider architecture. So there's a variety of functionality supported by the provider architecture, and our provider will provide key exchange in TLS 1.3, both hybrid and pure post-quantum key exchange, as well as hybrid and pure authentication in TLS 1.3, and hybrid and pure signatures in a variety of places throughout the OpenSSL functionality, including CMS, X509 certificates, and related import and export formats. And this functionality becomes progressively available based on the OpenSSL 3 version that you are actually working with. Michael Bench gave a talk yesterday at the OpenSSL conference, and I think he's there for the rest of the week. So please do take a chance to talk to him about the great work that's going on with OpenSSL 3 provider. So this kind of raises the question of the interaction and relationship between OpenSSL and OQS. So I think it's really great to see the NIST PQ standards available in OpenSSL 3.5. I think that's going to bring post-quantum cryptography to so many people who rely on OpenSSL, and I think the goal, and help us work towards the goal of achieving quantum-resistant security for the wide internet community. And so I'm looking forward to seeing great continued growth of PQ within OpenSSL. With OQS Provider, it still provides post-quantum algorithm support to users who are relying on earlier versions of OpenSSL 3. So OpenSSL 3.0 to 3.4 can still get some post-quantum algorithm support from Provider. So there's a great use case for it there. And we're hoping to have OQS Provider continue to bring support for these experimental post-quantum algorithms to OpenSSL users so that they can continue to test and evaluate post-quantum algorithms as the state of the art for post-quantum cryptography continues to evolve. We're continuing to develop OQS Provider, and we're really seeking more participation from the community, both in contributing and maintaining, as well as identifying directions that users would like to see the project go in. So we know some of our community members are interested in seed support and different private key formats. We also know of interest to use implementations from a provider like OQS, even when the algorithm is already supported in OpenSSL via 3.5 or higher. So it would be nice to be able to have those abilities going forward. And as I said, we're looking for participation from the community. We're going to have a call on October 23rd for solicitation of feedback and interest of participation from the community. So this OQS Provider community call is open to everyone, and we hope you'll be able to join us at that point in time, or if you're not available, then to pop in on our GitHub and let us know what you're interested in. So we'd really like to have contributions of ideas and codes to our project and hear what kind of features you'd like from the project. So we'd really be open to involvement. As I mentioned, there's the OQS Provider community call in a couple of weeks. Norm Ashley from Cisco and Michael Bench are at the OpenSSL conference this week. So please take a chance to talk to them. You can pop in on GitHub or one of our weekly calls. We'd just really like to hear from people. Now, our project is taking place within the context of an umbrella organization called the Linux Foundation, which is a not-for-profit organization hosting many open source projects. And in 2024, they spun up a new foundation within the Linux Foundation called the Post-Quantum Cryptography Alliance, which is trying to advance the adoption of post-quantum cryptography. And the Open Quantum Safe project is one of two major projects at the current time within the Post-Quantum Cryptography Alliance. So I also wanted to talk a little bit about our sister project, the Post-Quantum Code Package project, which is focused on creating and maintaining high assurance implementations of standards to track post-quantum cryptography algorithms. So I'll tell you a little bit more about their projects in a moment. But all of the work that's being done in the Post-Quantum Cryptography Alliance, the Linux Foundation, is being done under open source licenses, all with open participation on GitHub, and everyone is welcome to get involved. Organizations can also join as members to further influence the direction of the Alliance, but for the software projects themselves, like OQS and the PQ code package, participation is open to everyone. So now I wanted to also tell you a little bit about our sister project, the PQ code package. And there's some great work being done here by the whole team working on PQ code package. And it's being led by Hanno Becker at AWS and Matthias Kannemisker at Shelbless Quantum Corporation. So PQ code package is focused on creating high-speed, high-assurance implementations of post-quantum cryptography algorithms, the NIST standards that have been published and will soon be published. And the focus here really is on production-ready code that has high security assurance. So we're really looking for constant time, formal verification where possible, but also able to be used on a variety of languages and platforms. And again, the focus here is on open source software. So the default license is Apache 2, but some of the projects have a multi-license approach, so they can be used under a variety of licenses. There's several projects going on within PK Code Package. I'll talk more about MLChem Native, which is their flagship implementation of MLChem, but there's also work going on MLDSA, stateless hash DSA, and other MLChem implementations from other formally verified tool chains, the Jasmine tool chain called libjade, and a Rust formally verified tool chain called libcrux. But the flagship project within PK Code Package is MLChem Native. So this is a secure and fast portable C implementation of MLChem, starting from the original reference implementation of MLChem. And in terms of the security assurances that it has, it's aiming to have memory safety and type safety, and it uses a tool called CBMC, the C-bounded model checker, to assess the correctness, the validity of these claims. There's also assembly code for currently the ARM64 platform, which has some functional correctness proved using a tool chain called WholeLight. And there's also constant time testing for a variety of characteristics, including absence of secret dependent branches, memory access patterns, and variable latency instructions. And already MLChem Native is seeing some adoption. So it's used in Amazon Web Services, Crypto Library, AWS-LC. It's now being used in Russell's, the Rust TLS library for the MLChem implementation there. And we also use it in libOQS. And already some third parties have already gotten CVP certificates as well for MLChem Native. Now, I spoke a bit about formal verification being one of the features of MLChem Native. So I wanted to tell you a bit more about how they're doing that. So for the C code, the goal is to prove type safety and memory safety. So assuring, for example, that there are no overflows. And the tool that's being used for this is the C-bounded model checker, CBMC, which is an existing project. So what they do with this CBMC is to create contracts for every C function in the project, in the software, and then try to derive automatic proofs on a per function basis for verifying these contracts. And this involves invariants as well for how the functions behave. And this covers all the C code in MLChem for the both the MLChem code itself, as well as the SHA code used for hashing. And this is a key part of the overall development process, and rechecking of the CBMC proofs runs during continuous integration on every committed change. There's also assembly code in there, and there's formal verification applied to the assembly code as well. So in particular, that the object code produced after assembly implements the mathematical spec. And the tool being used for this is WholeLight, which is an interactive theorem prover. This requires manual proofs for every assembly function that's provided. So this is a fair bit of manual work, but currently there is coverage for all of the ARM64 assembly code present in MLChem Native. And an upcoming goal for the project is to extend this to the x86-64 platform. And again, this also runs during continuous integration to re-verify that the proofs continue to hold. In terms of future directions for the PK Code project, the PQ code package project. In MLChem, they're working on new backends for a variety of target architectures. So 64-bit RISC-V and PowerPC 64 little endian are coming from Markku Saarinen and IBM, respectively, as well as M-Profile, vector extension, and Helium code from ARM. So MLChem native is already fairly far along. MLDSA native is a work in progress project, aiming to achieve the same goals as MLChem, and they're working to close performance gaps and hope to have an alpha release in the next few months. So what we're seeing in PQ code package is these standalone, high assurance implementations of MLChem and MLDSA. Which can be integrated into a variety of cryptographic libraries. We use them in libOQS to support the standards track algorithms. And then we also, in libLQS, an OQS provider, have support for the many more experimental and future post